Hello, everyone. I hope you're having a great day and thanks for attending this event. My name is Michael. I work at the International Sales Department of WEG Automation and I'm today's webinar host. This webinar will be presented by my colleague Altair Groth Jr., who is a sales engineer with almost 10 years of experience in automation. He will be talking about solutions to mitigate the impact of long cables in the installation system of motors when driven by variable speed drives. Before we start, I have some information about the webinar. If you have any question, you can write it in the questions and answers chat in the streaming platform. The webinar will be recorded, meaning you can watch it later or send it to someone else. To do so, just go to WEG's LinkedIn page and click on events or visit our YouTube channel. There you will find this past and future webinars. Please follow WEG's page on LinkedIn. We share updates about WEG product solutions and our webinars there. Last but not least, I'll be soon presenting a webinar about harmonics and how to mitigate them. So stay tuned. Without further delay, Altair, take it away.
Thank you very much for this introduction, Michael. So my name is Altair Groth Jr. I will be presenting this webinar today. I hope you're having a great day and let's learn something about filters and drives here in this webinar. So let's get started. Today's event will follow this agenda. First, it will be talked about the basics of variable speed drives to give us the general knowledge of how it works. Then, it will be spoken about motors driven by VSDs and the effects on the motor and insulation system. Later, how long cables impact the insulation system by amplifying the effects of VSDs when driving electrical motors. Finally, it will be presented ways to mitigate long motor cable applications. So, first of all, what is a VSD? Variable speed drives are electronic equipment designed to vary the speed of the motor via the variation of its output frequency. They work as an interface between the energy source, AC power line, and the induction motor. It can also be called by several other names, but not limited to variable frequency drives, adjustable speed drive, adjustable frequency drive, and also inverters. How does a VSD work? In order to obtain an output signal of desired voltage and frequency, the input signal must go through the inverter. The typical construction of a low-voltage VSD is comprised of three main parts, or stages: the rectifier or diode bridge, then the DC link or filter, finally, the inverter or IGBT power transistors. The diode bridge is responsible for the rectification of the AC input voltage of constant amplitude and frequency coming from the power grid. For example, in Brazil, a common three-phase grid in industrial plants is 380 volts, 60 Hz. The DC link or filter regulates and smooths the rectified signal with energy storage through the capacitor bank. In some cases, DC link reactors can be added to reduce the harmonic content by attenuating harmonics, here seen as L1 and L2. The power transistors make the inversion of the voltage coming from the DC link into an alternate signal of variable amplitude and frequency. Power transistors can be made of several types. WEG currently uses IGBTs as switching devices in drives, and it stands for insulated gate bipolar transistors that create a train of pulses PWM, which is the pulse width modulation. The IGBTs are controlled in such a way that they can generate a variable voltage and variable frequency in the output. This is the signal that the motor will receive at its terminals. Let's now zoom in the VFD's last stage to understand better its operation. The following waveform depicts the behavior when varying the width of the PWM pulses. This curve shows a signal of a frequency f where the pulses have predetermined widths to recreate a sinusoidal waveform. The wider the pulse, the higher is the voltage in a given curve. On the contrary, the thinner the pulse, the lower is the voltage delivered. What makes a pulse wider or thinner is the duty cycle of the switching device, in this case, the IGBT. By dividing the cycle length of the first graph by 2, the second curve has a frequency of 2f. By dividing again the cycle length by 2, the third curve's frequency is 4f. And these frequencies impact directly in the motor speed, as we can see in the motor speed formula. The higher the frequency, the higher the speed, as speed and frequency are directly proportional. The other two factors that could be varied to control the motor speed are the motor slip, represented by S, and the number of poles, represented by P. However, they bring several disadvantages instead of varying the motor's input frequency. Motors driven by VSDs, or in other words, with speed variation, can deliver several benefits to the application. First, remote control. The control can be installed remotely at a suitable location, keeping just the motor in the processing area, on the contrary of hydraulic and mechanical varying speed systems. Gain of productivity. Industrial systems are often oversized due to an expectation of future production increase. Static inverters allow the proper regulation of the operational speed according to the equipment available and the production needs. Energy efficiency. The power system global efficiency depends not only on the motor but also on the control. Static inverters are high efficiency equipment, reaching typically 97% of or more. Induction motors also present high efficiency levels, reaching up to 95% or even more in larger machines operating at rated conditions. When speed variation is required, the output changes in an optimized way, directly affecting the energy consumption and leading to high efficiency levels performed by the system. Inverter plus motor. Because of this advantage and many other, speed variation by frequency control is the most popular method that can be found these days. However, motors driven by VSDs through PWM technology face some effects that can lead to damages if not taken into account. Rise time lead to voltage spikes. Common mode current flows in the bearings. Also, there are other effects such as the switching frequency of the IGBT. It's important to learn about these factors and effects because when motors are driven by VSDs with long cables between them, these effects are amplified and they have to be dealt with accordingly. Let's take a look at each of these components. One of the main factors that impacts in the motor service life are the voltage spikes generated by the rise time. For the transition from the minimum value up to the maximum level, the PWM voltage signal takes some time, which is called rise time. Due to the high switching speed of modern IGBTs in inverters, the rise of front wave of voltage passes too fast, and with the new discoveries on power electronics, the transition times tend to decrease even more. With the great speed of the pulse of voltage emitted from the inverter to the motor, the first turns of the first winding of a given phase are subjected to high voltage levels. Due to the inductive and capacitive characteristics of the motor's winding, the pulses are dampened in the subsequent turns, thus creating a larger potential difference between turns and damaging more quickly the insulation system of the motor. Therefore, the rise time can be extremely harmful in the service life of the motor's insulating system, because the lower is the rise time of the pulse, the bigger is the rise time rate, called dVdt. Due to the high voltage gradients which the insulation is subjected, the motor must have superior dielectric characteristics for this application when it's driven by a VSD. The definition of rise time, TR, can be defined by NEMA and IC standards, which can create interpretation divergence and conflict between manufacturers and users of electrical motors and VSDs. Because WEG's criterion is based on NEMA, it will be presented only in NEMA's definition to prevent further confusions with the different definitions. Rise time is the time needed for the voltage to rise from 10 to 90% of the DC link voltage, roughly 1.4 41 of the drive rated voltage. According to NEMA criterion, the DC link voltage must be taken as 100% voltage reference for determining the rise time and the calculation of dVdt. The rise time value is a data to be informed by the inverter's manufacturer. Here we have an example of a motor's data sheet which was designed to be used with an inverter. Let's make the calculation using this motor's data. The rated voltage is 440 volts. This way, the VDC link is 620.4 volts. So the delta V, 620.4 volts times 0.8 equals 496.3 volts. This 0.8 represents the 80% of voltage to go from 10 to 90% of the DC link voltage. The drive's rise time is 0.1 microseconds for CFW11, for example. The dVdt is 4,963.2 volts per microsecond, which is okay to this motor, which can withstand a dVdt up to 5,200 volts per microsecond. Besides the effects caused by the rise time, there is also the frequency at which they are generated. Differently from eventual impulses caused by power grid operation, it's about the pulse train carried at a certain frequency. Thanks to the fast developments on power electronics, nowadays this frequency reaches values up to 20 kHz. The higher the switching frequency, the faster the degradation of the motor insulation takes place. Studies suggest that there is no simple correlation between the insulation life and the switching frequency, in spite of the experiences have shown interesting data. If the switching frequency is equal to or lower than 5 kHz, the probability of insulation failure occurrence is directly proportional to the switching frequency. If the switching frequency is higher than 5 kHz, the probability of insulation failure occurrence is quadratically proportional to the switching frequency. Another motor damaging cause is the common mode voltage and, as a consequence, current. The three-phase voltage supplied by the PWM inverter, differently from a purely sinusoidal voltage, is not balanced. In other words, due to the inverter stage topology, the vector sum of the instantaneous voltage of the three phases at the inverter output does not cancel out, and it results in a high-frequency electric potential relative to a common reference value, usually the earth or the negative bus of the DC link. It is from there that the name common mode comes from. Here we have zoomed in the common mode voltage. This high-frequency common mode voltage results in undesirable common mode currents. Existing stray capacitances between motor and earth may allow current flow into the earth, passing through rotor, shaft, and bearings, and reaching the end shield, which is earthed. Practical experience shows that higher switching frequencies tend to increase common mode voltage and currents. Equivalent circuit of the motor for the high-frequency capacitive currents are shown here. Here, a little bit more detail of the common mode current impact on the bearings. The rotor is supported by bearings, which have a film of non-conductive grease. At high speeds, there is no contact between the rotor and the outer race of the bearing, which is grounded, due to the flat distribution of the grease film. The rotor potential can then rise relative to ground to a level capable of breaking the grease film. Sparking occurs and discharge current flows through the bearings. This current circulates when the grease film is momentarily broken and it's called capacitive discharge component. These discontinuous electric discharges wear the raceways and erode the rolling elements of the bearings, causing small superimposing punctures. Long-term flowing discharge currents result in furrows or flooding, which reduce bearings life and may cause the machine to fail precautiously. Now that we have spoken about some effects caused by VFD-fed motors and its PWM signal, we came to the point to explain the effects caused when motors and VSDs are connected with long cables. Besides the rise time, the cable length is a predominant factor influencing the voltage peak occurrence at the motor terminals. The cable can be considered a transmission line with impedances distributed in sections of inductance, capacitance, series parallel, connected. At each pulse, the inverter delivers energy to the cable, charging those reactive elements. The signal reaches the motor through the cable and is partially reflected, causing overvoltage, since the high-frequency impedance at the motor input is greater than the impedance of the cable. Differently of what is thought, the propagated and reflected signal do not cancel out. Instead, the pulses are added. This way, elevated cable lengths generally increase the overshoot value at the motor's terminal. According to the NIM application guide for AC adjustable speed drive systems with modern IGBTs, overshoots begin to appear from approximately 3 meters of cable, and it can reach several times the value of the source voltage for long cables. In this slide, we can take a look at the effects in the line voltage as the cable length increases. When we add a 20-meter long cable between the motor and the VSD, the voltage spike increases as well, reaching almost 630 volts. With 100-meter long cable, the voltage spike can reach almost 1000 volts. That's something that the motor's insulation system has to withstand, or something else has to be done. The rule is quite simple. The longer the cable, the higher the voltage spike. The values presented here are only examples, because the overshoot levels depend on the type of the cable being used too. WEG induction motors to be driven by VSDs or WEG VSDs are designed and constructed to withstand the PWM effects in applications up to 100-meter long cables without any additional equipment. But what about applications with longer cables than 100 meters? Well, these applications may require special equipment called output filters, which are commonly installed inside the VSD panel and very close to the drive. So, the main function of this additional filtering equipment is to strip certain frequencies from the voltage waveform. There are three types of filters that can be applied in applications with cables longer than 100 meters. They are, first, the output reactor, the simplest one. The DVDT filter, a bit more complex and with additional benefits. Finally, the sine wave filter, the most robust. Each one of these filters possesses advantages and trade-offs. Now, let's take a look at each one of them. The first one is the three-phase reactor, which is basically an inductor connecting series between two voltage points in the system. The reactor has an internal impedance capable of reducing line voltage distortion and reducing current peaks on the bus, once the current does not undergo sudden variations in an inductor. Another name for it is load reactor. With the addition of the output reactor, standard drives can run motors located from 100 to 300 meters away. That's a great advantage because it is 3 times longer than in assemblies without any filter. The downside of the reactor addition is the voltage drop of 2 to 3% in the reactor. The next type is the DVDT filter, which consists of a LC filter used between the VSD and the electric motor. This is designed to define the frequency band tolerated on the bus, configured in low pass in order to filter the frequency and reduce electrical noise. The DVDT filter is comprised of a bank of capacitors connected in star and line inductors. This filter allows a better protection on the load side against voltage spikes and common mode voltage. For example, it reduces more than 50% of common mode. It provides protection against voltage spikes and rise time reduction all in one filter. Also, it has low power losses which reduces the heat up of the system. Finally, it's rather quiet when compared to the next filter. By applying the DVDT filter, the resulting current at the motor's terminal is a clean sinusoidal. The maximum length of cables can reach 500 meters, which is 5 times the standard distance when you're not using a filter. The voltage drop can be calculated using the formula below. The voltage drop equals 2 times P times frequency of the VSD output times filter inductance times current. In average, the voltage drop ranges between 2 to 5%. And the last filter is the sine wave filter. Like the DVDT filter, it is a LC filter as well. It is designed to let through only low frequencies. Its difference in relation to the DVDT filter is in the design of the inductors and capacitors. The L and C in the sine wave filter are designed with values of greater magnitude, mainly in the capacitors, which makes it much more efficient. On the other hand, the cost of its implementation is higher compared to DVDT. In this way, its ability to reduce voltage peaks and noise in the network is greater, allowing the distance between the VSD and the electric motor to be greater than previous filters. Just like any other filter for the protection of electric motors, the sine wave filter is installed at the output of the VSD. This results in an even cleaner sinusoidal when compared with the DVDT filter. The distance between the motor and the VSD can be up to 1,000 meters, so 10 times the standard distance between the drive and the motor when you are not using any filter. The voltage drop can be calculated using the formula below. The voltage drop equals 2 times P times frequency of the VSD output times filter inductance times current, which is the same formula we used for the DVDT filter. In average, the voltage drop is between 10 to 15% in traditional sine wave filters, but more modern filters can reach lower values. To wrap up, here we have important information to be aware of when selecting the filter for your WEG motor when using CFW11 drives, for example. On this table, we have a comparison of all filters that we have presented in this webinar. These values are typical application distances based on WEG's experience in several practical cases suitable for WEG motors and WEG VSDs. For a deep analysis, it is needed to take into account all the characteristics of the system. If needed, contact your local support. Other considerations when sizing the output filter. As cable length increases, the effect of leakage current increases and must be considered when sizing the system. Filters and long cables cause a voltage drop and increase motor current. The sine wave filter does not allow vector control, only scalar. For drives with step-up transformers, it is necessary to use a sinusoidal filter. Now, let's move on to another way to solve the long cable problem. WEG's newest range of VFDs called CFW900 has an option for PWM modulation, especially designed for long cable applications. By selecting this PWM option, it allows you to extend the length of the cables used on the output of the VSD to drive the motor. You question, how long can the cable be? 200 meters without any output filter. This is valid taking into account the insulation system used in WEG or equivalent motors. Also, the immediate question that comes to your mind is, what about using this function along with output filters? Is there any additional advantage? The answer is yes, there is, but we'll talk about it in a minute. First, let's see what happens when we use the PWM modulation for long cables. Through the image, you can see a direct comparison of the difference between not using the PWM modulation for long cables and using it. These measurements are real and carried out with the WEG inverter CFW900, connected to a WEG motor with a cable longer than 200 meters. In dark blue, we have the voltage at the output of the VSD, and in light blue, we have the voltage at the motor's terminals. Note that in the image on the left, there are several voltage peaks at the motor's terminals. These voltage spikes are a normal result of the modulation process, but their overshoots are increased as the pulse is thinner. In other words, when the duty cycle of the IGBTs is shorter. Now, the image on the right. When the modulation function with long cables is enabled, with exactly the same cable distance, the same motor and VSD, the voltage peaks have been reduced. How does it work in practice using the CFW900? It's quite simple. There are only two parameters to be set on CFW900 to configure the PWM modulation for long cables. The first parameter is to enable the long cable modulation suitable for application with long cables. On C1.4.1, select the option 2. Then, it is required to set the minimum duty cycle allowed in the switching of the inverter on parameter C1.4.4. The default value is 0.15, meaning that pulses equal to or lower than 15% of duty cycle are removed. Thus, the worst overshoots are eliminated as well. In order to see the effect better, the results were exaggerated and these curves are merely illustrative. The pulses in red represent those pulses that were removed by this setting. It is important to note that during the several tests performed at WEG, it was not seen any significant increase in temperature of the motor, which could be an expected outcome, in spite of the distorted curve generated by this function. So with this new function available on CFW900, this drive can run motors up to 200 meters of cable without any type of output filter or reactor. And yes, this function can be used in conjunction with output filters. In case of using one of them, cable lengths can be increased up to 500 meters with regular output reactors and up to 5 kilometers of cable using a sine wave filter. You may think it's too much, however, it's common in submersible pumps in the oil and gas segment. The main advantages of this new function are up to 200 meters, no additional component is needed, saving panel space and makes smaller cabinets. Also, it gives a more competitive solution. The simplification of the VFD panel means fewer components, less wiring, and less labor. Up to 500 meters, a simple component such as a reactor can be used instead of DVDT filters, making the solution more competitive in cost. Up to 5,000 meters, using the PWM modulation function with a sine wave filter, the drive can run motors in very long cables application, such as submersible pumps and others. Thanks for joining us today for this webinar. I hope you have learned something valuable for your professional life and WEG will be waiting for you in our next webinar. Bye.